Here's our example of project part 4. All right, so with this project, it's very similar to lab 10. If you haven't done lab 10, that's fine. It's actually a relatively simple calculation, so I'm going to go through this. All right, so the basic idea is to take the distance that your planet is. So you're going to do it for your planet A, planet B, and planet C. If you look up in part 1 of project part 1, it'll give you the distance, right? That your planet is from from its sun, its star, and so you just look that up, and that A goes right here in this equation. All right, so it's literally as simple as that. And so you do this calculation, and this is basically the temperature. If it's the temperature that a planet would be at, right at the at the upper atmosphere of that planet, if it has an atmosphere. Actually, that's what we're going to calculate. Is the temperature that just the solar temperature, the temperature that comes from the radiation coming off of that particular star. Now keep in mind that what we're doing here is not entirely accurate, of course. What we're doing is we're using this figure right here, which and this number right here and this number right here, which basically comes from our solar system. These are properties of our solar system. So, in reality, in another solar system, you'd have a different. This number here, the 6,000 Kelvin, is the surface temperature of our sun, or approximately the surface temperature of our sun. It's more like 5,800, but that's fine. We generally use 6,000 Kelvin, and that's what we're going to use for this project. That's the 6.96 times 10 to the 8th meters. That's the physical size of our sun. And this 1.5 times 10 to the 11th meters, that should be in meters down there, that is what one astronomical unit is. That's the distance between the Earth and the sun in meters. All right, so you multiply your particular planet A, planet B, planet C times that number. All right, so let me just show you how to do this, and then basically, once you get the solar temperature, you're going to look up and find what you had already calculated the escape velocity for your particular world. That comes from the last project part 3. So you're going to look that up. Make sure you just look it up. I will have provided the answers for project part 3. And so you just look up that number especially like if you got it wrong, use the number from the actual answers. And then what you do is you take 6 times the molecular speed, and we're going to look this up. We'll look up what the molecular speed is for these different molecules. So let me go through the molecules real quick. So these are the common molecules that we find in our solar system and even in other solar systems, as a matter of fact. Hydrogen, this is, of course, this is molecular hydrogen, H2. All right, so anyhow, molecular hydrogen, helium, this is ammonia, CH4. This is, I'm sorry, CH4 is methane. This one, NH3, that's ammonia. And that's, of course, water. N2, that's nitrogen. O2, that's oxygen, and this, of course, is carbon dioxide. The last one's carbon dioxide. So these are the common molecules that we'll find. And the basic idea here is that if 6 times the molecular speed is less than the escape speed, those molecules will stay in the atmosphere. All right, so you got to look up the escape speed, and then you got to look up. You got to figure out what 6 times the molecular speed is. You get the molecular speed from the solar temperature. All right, so I'll show you how to do that. All right, so this is the list of planets, right? There's planet A, these are planet A, here's planet B. And so you're looking up this column, which has the distance from the star, right? And for mine, I'm going to do this last row, which doesn't have a student's name, and I'm going to choose planet C for that row, for that particular row. So my planet C would be 0.05 astronomical units. Okay, so that's what we're doing. All right, so I already have it set up right here. So you have to calculate the solar temperature. All right, and so we always use this formula, but then you put in the value of your particular A for your planet. All right, so mine happens to be 0.05 astronomical units. All right, so let's do this calculation. All right, so the calculation looks like this. All right, so yeah, I'm gonna put these numbers. All right, so it's going to be 2 times 0.05. Right, so I'm doing the denominator first, times 1.5 times 10 to the 11th. All right, so that's the denominator. Well, once I hit enter, so 15 billion. Okay, so I'm going to store that in my little calculator here. So just to remember that. And remember, this is the physical size of the sun. So, the only thing that changes is A in this equation. So it's going to be let me just type it, 6.96 times 10 to the 8th, and then divided by, and remember, I just stored that. So I'm going to divide by that thing that I had stored, equals, all right, and then I take the square root of that, and then multiply it by 6,000. And 6,000, of course, is the surface temperature. 6,000 Kelvin is the surface temperature of our sun. All right, so take the square root. So that's this button. So there's the square root, and then times 6,000. All right. So even though this particular planet is only 0.05, I mean that's for example much closer than Mercury, for example, is about 0.4 AU. So this planet is much closer to its star than Mercury, but and so it's going to be its temperature that it receives from the sun is okay. So it's 1,292. All right, so that's really important. I'm going to write that down. So that's my solar temperature. All right, for my planet C. So what was it again? Hold on, let me. All right, so this is what we get. It's 1,292. All right, and just because of the way that you'll see when we look at the table, we're going to have to round that to 1,200. All right, so you'll understand. I just didn't do a calculation for 1,300. I probably should have, but that's fine. You see how you would see that 1,292 is closer to 1,200. It's closer to that than it is to 1,300. All right. So now, and the other thing that I did is I looked up. So you do this right on your own. You look up the answers. Okay. So I've provided the correct answers for the escape velocities. Remember that you did that in project part 3. The escape velocity in kilometers per second of planet C. So for the one that I looked up where, the distance between the planet and the star is 0.05, when the correct calculation for the escape velocity turns out to be 23.5 kilometers per second. So these two pieces of information is what we need to complete this lab. To complete this project. Which of course was very similar to Lab 10. All right, so we need this rounded solar temperature. You'll see why we round it in just a second. So 1,200 Kelvin. So keep that in mind, and then 23.5. All right, so then the rest of it is just looking at the table. Well, you got to multiply by 6. You'll see. All right, so let me set it up. All right, so here we are. This is again the project. So you've looked up your escape speed for for each of your planet A, planet B, planet C from part 3. Anyhow, remember you look up the correct answer because that's absolutely critical. All right, so you've done this calculation. You put in your. So let's see. I I did my planet C. So for me, remember, you use the rounded value. It's really important to use the rounded value, and I'll show you why that is. So you'd put 1200 right here. That's the solar temperature, right? That's this column. So 1200, and then, because I did planet C. And then for mine, this number right here would be 23.5. Okay, so here, I'll show you that in just a second. See, there it is. There's the 1200. There's the 23.5. So you're going to put that into the Word document. Now what you're going to do is you look back at the Word document, and so just scroll down. Okay, so I'm on the same row. Okay, so this is what we're doing. Okay, so this is an extension of Lab 3. I'm sorry, Lab 10. Sorry, I'm getting. So what you do is you say, all right, in yellow here, this bright yellow, you have across the top, and they're down here as well. Okay, so some of these, for some of these planets, for some of your planets, they're going to be really far from the sun, and so their solar temperatures are going to be really, really low. All right, so these are closer in planets. So ours was 1200. Remember how we rounded it to 1200. It's really between 1400 and 1200, but 1200 is closer, so we're going to use that. And then so you look down here. Okay, so hydrogen. So the hydrogen molecule at that temperature has a molecular speed. So these are calculations. You don't have to do this. You just look it up, right? So you find the 1200. There's the speed for hydrogen. There's the speed for helium. There's the speed for methane. There's the speed for ammonia. Okay, and water and nitrogen and oxygen and carbon dioxide. Okay, so those are the gases that we always deal with. It's the exact same gases, but you just multiply each of these numbers times 6, right? So 6 times 3.84. Okay, so I'm going to do that real quick. All right, so you don't even actually have to do a calculation. So if you just open this file right here, which says 6 times the molecular speed, that looks like this. Let me open it up. All right, so these are the molecular speeds over here. And then you see here, let me just show you what I'm talking about. So those are just the regular molecular speeds. And then this is what you're really interested in. So remember, our solar temperature was 1200 for my particular planet. And then 6 times, and it's exactly in the same order, right? Hydrogen, helium, and so it's 23, right? So that's the highest the highest molecular speed, and this is the lowest molecular speed for it's just because they're larger molecules, right? Remember, you can look over here. That's for carbon dioxide. That's the largest of the molecules. Anyhow, the size of the molecule. And the other thing is, I should point this out. When you see these little asterisks right here, at that particular temperature, those things are a solid. We're only interested in gases. Okay, so keep that in mind. So let's actually look at the top one here, since that's the highest temperature, 23. Remember, so that's 6 times the molecular speed at that temperature at 1200 is 23 These are in kilometers per second. It says it right here. So 23 kilometers per second. And we look at our example. So look, this tells us our escape velocity is 23.5. So for hydrogen, right, the molecular speed of hydrogen, or 6 times the molecular speed, right? 6 times the molecular speed. And this is the fastest one, speed, is greater than our escape velocity, right? It's greater than the escape velocity. Oh, I'm sorry, no, it's not. It's less. Let me hold on. Let me erase that. All right, so I corrected that. So these our 6 times the molecular speed is less than the escape speed. So since it's that is less, that molecule and all the other molecules. So here, let me go back to this. That molecule and all the other molecules at that temperature will stay in the atmosphere of that planet, right? Because they're all less than 23.5, which is, of course, the escape speed. All right. So that's how you do the problem. You do it with